performance. This is a cost function, loss function. You use it the minutes. But basically, during the training, you based on that thing, you update the parameters so that in the end of the day it will be better. So this is from 3 blue, 1 brown. So just check it. Google gradient descent, you'll find it. Very nice animation there. But okay, I will come back a little bit. One thing is, what is gradient descent? Okay, so you're starting from somewhere. So this theta actually, this is a very, very simple one. So this loss function, you only have one parameter, and this parameter is theta. Okay? Okay? And then this is the loss function, which is a function of theta. Basically, if you change the value of theta, you have different loss functions. Just like if we change the value of W1, W2, and B, which have three-dimensional things, right? But if we change the value of theta, we actually got different loss, right? So we somehow want the loss to be minimized, so we actually, the best theta here is this, right? So we can change the value of W1, W2, and B so that the final loss function is minimized. So this is like we only have one parameter, and how we change this one parameter to be, to minimize the loss function. And this is what we do in gradient descent. So in gradient descent, like every time step, we will compute the gradient, which is the direction that we want to go down, right? So here, the direction is like the gradient direction. So the gradient direction is like that. And then we move one step out. So eta t is like the step we want to move out. So we move one step out, then we add this stage, right? So after moving this, what happened? The loss function goes down, right? It's like we're doing an update on W1, W2, and B, and the loss function goes down, right? Then we do it for the second time, and we do it for the second time. We compute the gradient at that time step, and then go follow that direction, and then so on and so forth. In the end of the day, we'll go to the point where this is minimized, and then we find the best theta here. So we find the best W1, W2, and B there. So fortunately, so in this procedure, what we need to find is the gradient at that time step, right? So that is given to you by PyTorch. So as long as you have the computational graph, you are able to compute the gradient there, and then follow this gradient. You will be descent to the local optimal point, to the lowest point. Okay, so this is gradient descent. What actually behind this gradient descent? Okay, and of course, starting from different places actually means different things. So if you initialize the theta to be different values, then you follow the gradient descent. Sometimes you will be here, right? So for example, if you're starting some place like this, then you will go here. But if you start at some place like that, you'll go here. So it sometimes will be, going into the local minimum. Okay, but it's okay. We'll just randomly initialize our parameter multiple times, and then we compare, what's the final loss function value, and then we picking up the one which has the lowest loss function value in the end. Then we choose that as our model, right? So we choose this one rather than that one. Okay, this is how initialization change your final thing. Okay, so this is something about gradient descent. And something about training. I want to say this is actually some slides I created for the machine learning class. So machine learning is really like a black box these days. So you have some input and go through a model, which is your black box, and then go out, right? So you have some predictions. So the inference stage, which is like corresponding to the prediction, which is corresponding to the forward pass of the neural network. What we do here is we have the input and output, We actually have the function. We know what the model looks like. We know what the function looks like. And we want to compute some output there, right? So it's easy for us to compute the output given this black box. We know the configuration of the black box. We just throw the number in, and then it will throw some number out. Okay? So the training procedure is different. It's basically saying, I tell you, the model looks like this. So this is the model that we have. We have W1, X1 plus W2, X2. And then we see a set of training examples. We see a set of training examples. For example, we see if we give it 1, 2, it gives us 5.1. If we give it 2, 3, it gives us 8.2. If we give it 3, 6, it gives us 14.7 something. And what we're trying to do there is we're trying to guess W1 and W2, right? Someone take a guess. What is W1 and what is W2? Yeah. Take a guess. Ready? I got an answer when I was teaching machine learning course in like 2 seconds. Sorry? 1 and 2, right? W1 equals 1, W2 equals 2. What happened? 1 times 1 plus 2 times 2 equals 5, which is pretty close. We have 1 times 2, and 2 times 3 equals 8, which is pretty close as well. Some people told me it's W1 equals 1.1 something. It's really nice guess. You're doing gradient descent there, right? So what you're trying to do there is what? What are you trying to guess? Why are you guessing this way? You are actually optimizing these values. You are trying to find a good W1 and W2 here. And what is your criterion there? Your criterion is, I want this thing to be smaller. W1x1, sorry, plus W2x2. This is actually the prediction. This is the y hat, right? Your function's prediction. And I want this thing to be, if it's minus y, this number should be really small, right? This is what you're trying to do there. Why are you trying to find the best? When you're trying to find the best W1 and W2, you're trying to make this number small, right? Everyone agrees with that? When I put W1 equals 1 there and W2 equals 2 there, we have 1x1 plus 2x2 minus the correct answer, which is 5.1 here. And that gives you 0.1. And some people are not satisfied. They put W1 equals 1.1 there and W2 equals 2. So 1.1 times 1 plus 2 times 2 it's 5.1, and minus 5.1 is 0 there, right? So this one is better because it leads to a smaller number of the things, right? Right? Everyone gets the intuition there? When you're taking a guess, what are you trying to base on? This is a loss function, right? This is the loss for this task. And we are trying to vary in these numbers so that this loss is minimized. Right? This is what we're trying to do there. This is what we're trying to do there in this setting. So this is basically training. This is basically estimation setting. It's based on a set of examples. We're trying to find the best configuration so that our loss function there is minimized. And in fact, it's actually this, right? So in linear regression, if you know that in linear regression, this is the loss we're trying to do there. But anyway, right? So in that way, it's 0.1 square is 1.1. Sorry, 0, 0, 1. And if you actually put W1 equals 1.1 there, it's still 0 to the square. It's still 0. So it's still a lower loss you have there. But based on a set of examples, you're trying to minimize. You're trying to vary. You're trying to adjust those parameters to minimize a loss function here, to make this loss function smaller, to make less mistakes, to predict more accurately, and then this is training, right? So in supervised learning, in a nutshell, what we always have is, actually this slide is also good, is even you change this function to a more complicated neural network, it's the sum of the parameters inside this neural network, but you're still doing that. You're just changing those numbers to make this function a better one. And in a nutshell, this is doing what? This is doing supervised learning, where supervised learning have some essential things you will be having there. Supervised learning is probably where we spend 80% of the time in machine learning courses. It's like we will have some input x. So this x can be like, for example, two-dimensional, x1 and x2. It can also be like multi-dimensional, like a word vector, have a dimension of 512, something like that. And it's just a set of numbers. Okay, and you're trying to find a function. This function is f theta. Theta is parameters. It's parameters, right? So the parameters there can be w1, w2, v, whatever, wh, right? In the recurrent neural network, whatever, those kind of numbers there. And this function f theta x should map x to a prediction y, right? So at the very beginning, you'll be given a training set. This training set contains a lot of different examples for how human observe what's the relationship between x and y. Okay, so for example, if I say this sentence is like, this is such a great movie, then this is actually a positive label. So if I say this movie is like the worst I have ever seen, so this is why it's like a negative label there. So you have a bunch of this data that you are learning from. So this is where you get the supervision. So learning from supervision is learning from human annotation, learning from human knowledge based on this training set supervision. You're trying to estimate a better theta that does a better job in terms of mapping x into y. Okay? You're searching for the best function there that does the job of mapping x into y. This is supervised learning. Okay? So this is how we know we're actually doing a good job, is in the end of the day, when we compute our loss function on this training data set, it's actually very, very low, right? Meaning that we're doing a great job. Because if we're doing it wrong, the loss should be higher. If we're doing it correctly, the loss should be lower. That's why we say, P1, if I only put negative P1 there, it's also a good loss, because if we're doing correctly, then the loss goes down. If we're doing wrongly, then the loss goes up, right? So we want to minimize that thing. But we also say, like, if we remove the negative log thing, if we remove the negative from there, if we just say log P1, then it's a bad one, right? Because when you're doing correctly, you actually incur a very high cost. But when you do it wrongly, you actually incur a very low cost. So you're searching in the wrong direction, right? It's like originally you should be going downhill, but now you're going upper hill, meaning that in the end of the day, you'll be having a really, really bad model. Okay, so this is supervised learning. So the 4 examples we just seen, 5.1, 4.8, those things, the 4 examples basically is a small training set that we use to adjust the parameters inside f theta to make it a better model. Okay, questions? So when we draw this kind of a graph, it's actually we draw in there how we compute this loss. And once we know how to compute the loss, the computer knows how to optimize the parameters for us. That's the best in terms of minimizing the loss. Okay? So the optimization task is taken by the computer. Okay, questions? Hope that helps to explain things a little bit. So, okay, so that is a very simple case on logistic regression, and definitely we can have like more complicated functions. For example, we'll be having this deeper neural network, which actually got many different things here. So we have the affine transformer for to get H2 and H1, which write down as H1 basically equals to W1 X1 plus W1 2 1 X2 plus some B1. Okay, so this is how we get H1 and H2 equals to W2 1 X1 plus W2 2 1 X2 and plus some B2 something. But whatever, so this is some ways of computing the H1 and H2 there. So after you have H1 and H2, you put it into a tanh. So this is something like a cosine function, tanh. So tanh H1, and then this is basically adding some non-linearity there, and you get T1. And then you put in some other fancy expressions, log, some x, whatever it is, and in the end of the day, you compute the loss. The loss will be equals this. Anyway, simple. So it's just a neural network of multiple layers, but as much as it's doing the basic computations in these different layers, once you only have this final loss nodes, it should be easy for you to backprobe to every single parameter inside this loss, inside this neural network, so that this makes a good job in terms of minimizing the loss function there. Okay, so why people love neural network? Why people love neural network so much? Then those kind of things. Why people don't like this? Why people love neural network? Because this is simple, right? So you actually think about it. You're doing a search over functions. You want to find the best function that performs the task well, right? So if it's a simple function like this, the search space is actually quite small, right? So for example, if you have only a linear function, then it's only a bunch of functions that you are searching in, right? But if you have a neural network, then you have many different parameters. Then what happens? You can have a whole lot different functions to search from, right? So this space is quite large. So whatever complex patterns in your training data set, we can have this function to fit that well. Okay? So this is the only difference. So more parameters, more complex of the function, you have larger search space for this function, you tend to have a good result in the end. And a very important thing is the softmax function. So this softmax function is sometimes called softmax layer. It's basically where we get the probabilities. So it's easy for those things to get W1 X1 W2 X2 plus B, some kind of a score. Some kind of a score, it's easy, right? But if I have a score for class 1, say score 1, and I have a score for class 2, say score 2, have a score for class 3, say score 3, then we'll need to output a probability based on these scores, right? So I say for class 1, the score is like 100. For class 2, the score is like 50. For class 3, the score is like minus 50, something like that, right? So this is not enough because we want a probability from there. Remember that when we're predicting the next word, so say that we only have 3 words in this word, which is simple, and then we want to have this dice. We want to make this dice, right? We want to make this dice so that we say the probability of generating word 1 is like 0.6, and probability of generating word 2 is like 0.3, and so on and so forth. Those things. right? It's easy for us to construct the scores for different classes, but it's not easy for us to transform them into probabilities. So to transform this into probabilities, we're actually using this softmax activation function. Sometimes we call it softmax, sometimes we call it softmax layer, have different names for it. But basically, what it actually means is to transform these scores into a probability. So this sum up to what? This does not sum up to what? That's the case. Okay? So what we actually do is what? Is we use this function. What is this function? So let's say how we compute this thing here, right? Okay. So we have e to the 5.1 divided by sum over j equals 1 to k. How many classes we have here? 1, 2, 3, 4, 5. Okay. And we have e to the vj. Okay. So this equals to e 5.1. I write it out. So it will be e1 to the plus e 5.1 plus e to the 2.2 plus e to the 7 plus e to the 1.1 and equals 0.9. I don't need to compute that because I computed it on the right hand side. Okay, so this is what the computation looks like. This is softmax function. Why people love this? First of all, it normalizes things into probability sum up to what? Everyone can see that, right? And second, the larger this score is, the more probability it takes, right? So it's a kind of a monotonic function that transforms these scores into probabilities to work with. So when you transform it into probabilities, you can use like log loss and put it on top of it, and then you can start to train your neural network, and you don't need to care about other things. And what's the third best thing here is even you have a negative score. So for example, if I have two classes and the score for class 1, and the score for class 1 is say 3, and score for class 2 is -2. So if I doing like this kind of a normalization where I just use 3, where I just use 3 plus -2, then divided. Let's say this so that we see it clearly, right? If we do this kind of a normalization, it's wrong, right? So we have 3 divided by 0, then this is what? Nothing. If you have all positive numbers, this kind of normalization may be okay. But if you have negative numbers, then it's not okay. But e to the vi is always greater than 1. Okay? So what it does, it first transforms these scores into into positive numbers, and then normalize the positive number into a probability. So the higher this number is, higher the score is, the higher the probability is. So that's why we love this function. Okay? Everyone knows that? The softmax function. This is very, very important. This is basically the neural nets that we built days ago. Questions?
Why do we use E?
Why do we use E?
Can I use 2?
Can I use 2? Okay, so basically the question is, can we use say 2 to the di divided by j equals 1 to k and 2 to the ej? That's your question, right?
Yes.
It's a very good question. Can we use 2?
Yes.
Sure, right? Why not? We can use 2, right? So this is also like good for that it transforms these things into a nice probability there. And if you actually see this through, if you do a differentiation on top of this kind of functions, you will have E anyway in the end. Okay, so but like definitely you can use 2. It's okay. Other questions? Yes. What is the difference between the softmax function and sigmoid function. That's a really, really good question. It's a really, really good one. I will first answer another question, then go to that. So another question is why it's called softmax function? Why softmax function? What's a soft for? Okay, what is a hard max function?
Yeah.
If it's a hard max function, the output here should be 0, 1, 0, 0, 0. 0, 1, 0, 0, 0.
Yeah.
Because it's picking the max. It's picking the hard max for you, right? So this is why it's called a soft max function. Not entirely. Second reason, when this number goes quite large, it soon got dominate on this function, right? So it's really picking some kind of a soft max in this region. So that's why it's called soft max. And why we're not using a hard max after all? Because first, some people say hard max is not a probability distribution. That's wrong, right? It is, because it's 0, 1, 0, 0, 0. It's okay. Hard max is hard to differentiate. It's like, you know, the 0, 1 loss thing. That's the story. This one is better for differentiation. If we can come back to compute the gradient for those things and keep our machine running. Okay. So what's the another question is what's the difference between sigmoid function and softmax function? So especially in binary classification. Okay, especially in binary classification. So when we're talking about this thing here, let's say this is the thing. Oops, sorry. This is the sigmoid function that we're having here. So sigmoid function basically transforms this number h into some kind of a probability between 0 to 1. Right? So this is what sigmoid function does for you. What sigmoid function looks like? People may see that before. It looks like something like that. Right? So when h1 is greater than 0, then it's something, basically I think this is 1, right? So it's something that close to 1. But when it's like smaller than 0, it's something more close to 0, and this is 0.5. Okay, so this is sigmoid function. This does a good job of transforming the thing to probability. But this is only binary case. So if you have a multi-class case, then it's a problem, right? So you can't do it in the multiple cases because this is sigmoid only transform one function there. So there's actually a very subtle difference between using sigmoid function and using softmax function for binary classification. So for using sigmoid function, you actually only compute this one score. So this is kind of the score. Let's say this is the score for class 1. Okay? This is the only one score that you compute there. And if you're using softmax, then you will need to compute this H2. Let's say this H2 equals W1 prime x1 plus W2 prime x2 plus B prime. Okay, so this H2 is the score for class 2. Then what we're trying to do is we will doing a softmax on top of this, right? So in the first case, when you compute the probability for class 2, you're simply using 1 minus that. It's okay. But here, we're putting a softmax on top of H1 and H2. So this also gives us P1 plus P2 equals 1, right? So it's the same thing because it's normalized here. What's the subtle difference there? Can you guys see? The first model only has 3 parameters. And the second model has 6 parameters, right? So if you're using a softmax here, you're actually having lot more parameters for this thing. So you compute separate score for H1 and H2. and you're trying to optimize on these things, changing the number of W1 and W1 prime, W2 and W2 prime, and B prime, those things. You get the best model that's optimized for this neural dice here. So it's a binary neural dice, right? It's a binary neural dice have like two sets of parameters. Right? If you're using a sigmoid function there, it's only having one set of parameters. So this is the subtle difference. I think if you don't know logistic regression before, if you don't know sigmoid function before, you might feel a little bit lost there, but it's okay. So like, sigmoid function and the softmax function, we can both use it. It's just a way of like computing the final probability of different classes. But if you know that thing before, you will know in the logistic regression case, in the original logistic regression case, we're actually using sigmoid function. And if we put it into more of a neural net word, we use the softmax function, then there's a subtle thing that we're adding more parameters into the model. Okay? And in terms of the performance, more or less the same. More or less the same. If you have more parameters, yeah, you have the old story, more parameters, then you probably easier to overfit, you need more data to train, those kind of things. It's there, but for simple tasks, simple as this, it's basically the same. Okay? Questions? It's a very good question. Sigmoid function and softmax function. Not quite many people asked this before. I think I thought it for a while as well. I always get confused. Like for the binary classification, it seems like we can use a sigmoid. We can also use softmax. What's the difference there? If you write that down, you know what's the difference there. Okay. Other questions? So this is how we built the neural dice. This is neuralize our dice. So when we having this softmax function, it's easy for us to transform a vector of different scores into a probability over different classes, into probability over different words. So back into the case of recurrent neural network. This is the computational graph for recurrent neural network. What we are doing there is at each time step, so say xt minus 1, xt and xt plus 1, our input is looking like word embedding, right? And then we input this word embedding into some kind of a black box. And this black box actually having a set of different operations there. We put some nonlinearity inside those blocks, whatever. Then we have the parameters for that block. It's bigger A, right? So big A includes WH, WE, all these different kinds of things. But why I put three SAM A here? Because the parameters inside these blocks are the same, right? So it's always WH and WE and B, always those parameters inside this thing. So in the forward pass, what we are actually doing is based on the parameters, based on the input word embeddings, then we're trying to compute HT minus 1, HT plus 1, those things there. It's easy for us to compute those things. Okay? So this is the forward pass for recurrent neural network. Right? This is the computational graph for recurrent neural network. Then we're trying to use it. We don't have a loss function here yet, right? Because when we trying to train that thing on some kind of a task, then we know what the loss function looks like. And another thing is why this is orange. Why this word embedding is orange. Everything has a reason. Why this is orange. What's the difference between input and parameter? We have 4 different kinds of nodes: input, parameter, operations, and a final expression. Expression, we have a special one, which is the loss. Loss is like the last thing that we can use. And what's the difference between input and parameter?
Input is fixed.
Yes. Answer is quite simple. Input is fixed. You can change input. Right? You can change the input to make your neural network looks better. That's awkward. But like parameters, you can change it to make your neural network compute a lower loss there. But you can also compute, the gradients with respect to the input as well, right? Like it's following the same philosophy, just using the automatic differentiation. Then you actually know how to change your input to make the loss lower as well. Everyone agrees with that? So if my input is like, if I have a function, 1 times x1 plus 2 times x2 equals 5, and equals whatever, then like, I want this to be lower. So if I have x1 equals 3 there, I can change the x1 to be lower, so that the final number is lower, right? Something like that. So we know how to change our input to make the loss lower as well, just as we know that for how to change our parameters. What that implies is when you're having these kind of word embeddings, you don't know where it comes from even. But when you train this kind of neural network, for example, you train it on an RN language model, just like we did before, like we say in the GPT language model, we have some kind of transformer here, then we train it to predict the next word, right? So this is the task that we're training on. We can backprobe to this word embeddings as well, right? We can change the word embeddings. We can change the representation of one word so that the final performance actually goes better, right? This is exactly how we get those word embeddings. It's like word embeddings are just parameters inside those kind of neural networks, inside what kind of computational graph. We'll talk about like we have many different ways of having like this kind of computational graph to compute word embeddings. But then remember that based on some kind of loss, you can always backprobe to these word embeddings, and then you can get better word embeddings, at least for the task you train on, right? Might not be better for other tasks, but it's definitely better for the task you train on them, right? So that's why I put orange here. Is sometimes when we're trying to do, for example, using the RNN to solve like movie review, positive, negative classification, those kind of tasks, we probably just use the word embedding as fixed. We don't change them. They are inputs. Okay. But for other tasks, for example, if we're training on RN language model, or if we train GPT, then we having them as parameters. We can adjust them to be better. So just remember, this is only difference between input and parameters. It's just input, you can't change them. But for parameters, you can change them. So then I have this way of treating something as parameters or as frozen. So people like always talking about this, like I keep my large language model frozen there, and then I add something there, and I tune on that adapter so that in the end I get better model. Okay, so you can treat it as a fixed one as input, or you can change it. So what is word embedding? I realize I should probably mention it a little bit here so that you get an example idea of what it looks like. So for example, if we have a word cat, then we have a word embedding representing this word cat. We have a word embedding representing the meaning of this word cat. So this word embedding looks like what? So it's basically a vector, and each of them is a number here. So probably we have 0.5, minus 0.3, then positive 1.2, blah, 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 blah. We have this vector here. So this vector is the representation, the vector representation for this word cat, for the meaning cat, right? What does it mean? What does it mean? So this defines a space, right? Definitely. This vector is inside a d-dimensional space, depending on how many dimensions you have there. So we're trying to say, if we know the word embedding for cat, and if we know the word embedding for dog, okay, then these two things probably should be closer to each other than the distance between cat to MacBook. Okay, so that should be far away. Now cat and dog closer, right? If we have kitty is probably even closer to cat, okay, in that space. So basically, we encode the meaning of those words into a space where similar meaning words are closer in that space. When we're talking about sentence embedding, we can embed a sentence into this kind of vector space so that sentence sharing the similar meaning, for example, thank you and many thanks and thanks, all those sentences should be closer to each other in that space. Okay, so it's like a distance measured in those vector space is a distance, is a similarity measurement for their semantic similarity, semantic relations. Semantic means the meaning of the sentence. Semantic means meaning. Okay? Understand the intuition there? Okay, so word embedding, you can do a lot of like funny things because it's vector. So here I have a really funny example, which is king and queen, man and woman. So if you use queen and subtract king, then you get this. Queen minus king equals this in the vector space. And then you put that into woman, and you search this area, you probably will get man. Okay? So in an ideal world, in such space, it will be having this kind of relationships. For example, China and Beijing, if you're taking this and put it on Japan, you get Tokyo, and put it in German, you get Germany, you get Berlin, those things. Okay, so this is some funny operations that you can do on this on these things. And those word embeddings aren't. Some people may ask, if each dimension have a specific meaning. So, for example, if the first dimension means this is animal or this is an object, and the second dimension means if it's female or male or whatever, those kind of things. Not necessarily. Okay, so for most of the time, the dimension doesn't have any meaning there. So only the distance between these things matters. But like sometimes you can tell stories about the dimensions, of course. But when you train such things, you actually don't know. If each dimension is meaning some kind of a value for some of the attribute for this word, you actually don't know that. Okay? Questions? Questions? Where we get those word embeddings? If we train a language model, RNN language model, then we adjust those parameters. We actually having those different word embeddings as parameters inside our neural network, and we adjust them. Then we get a set of word embeddings. And hopefully, these word embeddings can mean the same thing as we discussed before. And why it should mean the same thing as we discussed? Why? So say, if we know, the next word is some kind of a word, then this word is cat. Okay? And this word is cat. Okay? So the word embedding for cat is looking like that. Okay? It's a vector for cat. And then imagine that we replace this word embedding cat with some word embedding dog. Then it will still kind of output the same value for the next word. Right? Right? But if we change this into some kind of an unrelated word embedding, which is pretty far away, then the output for that one might not be the next word anymore, right? So if we saying that we can replace it and does not affect the computation of the neural network, means that these two words may share the same meaning. Okay, this is the intuition back on those things. Not necessarily that way, but intuitively you can understand that way. So when we train this recurrent neural network model, you realize like I add some small things here. One node I add there is I add this negative log softmax. So in here, what is softmax? Here we are rolling a dice, right, and decide what's the next word, right? So we put in this softmax, so it becomes a probability of the next word, and then we actually know what the next word is, right? We actually know what the next word is during the training, so we actually know, what row to pick from this softmax. Okay, so for example, the softmax gives us word 1, word 2, word 3, word 4, or whatever. So this is 0.9, and we actually know this word 2 is the correct word. So we put in this 0.9 here. Right? We put in to do log 0.9 and minus log 0.9, and we compute the loss here. Right? So this is the first loss that we have using x t minus 1 to predict the next word, which is xt. Okay, so the second time, what we do is we're using this xt and the previous history to predict the next word. Next word is xt plus 1. So we also know after we rolling this dice which word to pick there. So for example, we pick the fifth word. So the fifth word, the probability for that is a new one, of course. It's for 0.5. So we have the 0.5 here, then we have log negative 0.5, and then we put it into another loss. So in the end of the day, we'll do a summation over all these losses, and this becomes the final loss of the computational graph. That's where we start to do gradient descent from. So we'll be computing the gradient with respect to the loss to every single parameter that we have inside this neural network, and then we'll backprop from it to make it better. Okay? And it includes the word embeddings that we have here, right? It includes those set of parameters as well. Okay? So this is what we see in the last lecture. It's like we have all this computational graph, and what we're trying to do here is we know what's the parameters inside this RNN. So we have the WE, WH, and E1, and those E1, E2, E3, those things as well. So these things have the parameters, and then we will be adjusting those parameters based on the loss that we incur in every time step, and then we're summing up it into the final loss, and then we do a back propagation to change those parameters so that it becomes the best in terms of predicting the next word at each time step. So this is how we train RNN. Okay? Questions? Yes? How we set on the length of embedding, how we set the dimensionality of embedding, right? So that's a good question. So what dimensionality you want to set there? 100? 200? Yeah. So intuitively, the smaller the dimension is, the less meaning you can represent there, right? So it will be a clouded, more clouded space that you guys are competing for each other, right? When you have a larger dimensionality, and hopefully you can encode more information, more knowledge inside that word embedding. Okay, so this is really an empirical choice. But remember that. So by choosing a large dimensionality for your word embedding, you actually have large parameters inside this model, right? So for example, if you have a vocabulary size of 100 and you choose a word embedding dimensionality to be 100, then you already have 10,000 parameters. Everyone understands the computation? If you choose the word embedding size to be 100 dimensionality, to be 100 dimension, the word embedding, and you have vocabulary size of 100, then you already have how many parameters there? 100 times 100 parameters inside that matrix, right? So, what? Question? Question? Yes.
We have output layer in softmax function. So what's the output layer in your network?
Uh-huh.
How do you get the
How do you get the
output layer?
output layer? That's a really good question. So, so from this H1 here to this, say, Y hat 1 here, so you want this thing to be a dice, right? You want this thing to be a dice, so it have to consider it has to be a vector of vocabulary size, right? This has to be a vector of vocabulary size, and then after you putting this into a softmax, it produce the probability for you, and this is also vocabulary size. Then you should have like 0.5. I'm choosing like the first word and these kind of things, right? So in the end of the day, from this H1 whatever, you want to get out of a vector. Let's just call it Y1 hat. You want to get out one vector like that, and this vector is the dimensionality for that is vocabulary size, right? Whatever dimension for this has to be the dimensionality for the vocabulary size. Okay? How do we transform a vector of say size A to size B?
Linear transformation.
It's actually a linear transformation, right? For a vector into another, right? So if we have a vector of say this is the dimensionality for that is A, and we want to transform it into a dimensionality of that is B. How do we do that? We can use A times A times B equals B. It's why we need a linear algebra for that. But let me just write it down so that you get the thing. So say that in our first vector you have say x1, x2, x3. Let's call this vector x5, right? And you want to transform it into another vector x1 prime, x2 prime, blah 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 blah, until like x10 prime. So x2, say prime here equals what? It's a linear combination for these 5 numbers, right? So you can have x2 prime equals to some kind of this one plus this one plus 3 x3 plus blah 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 plus a b2 there. We don't have enough space for that. But each of these numbers is a weighted combination of the left-hand side numbers, so that it considers every single dimension in your first vector when transform into another vector. So this is an affine area. Sometimes when people are talking about neural networks, this is a fully connected area. This is an affine area, whatever it is. It's basically transforming a vector of dimension 5 into a vector of dimension 10. Transforming a vector of dimension A to a vector of dimension B. How many parameters you have in this transformation? For each of them, you will need 5 plus 1 bias, right? So for each of them, you will need 6. For each of this transformation, you will need 6, and you will need 10 of the different transformations, right? So in the end of the day, How much you have? How many you have?
60.
Yes. Yes. So this is the parameters that you introduce in order to put this size of vector into another size of vector. Okay. So if you know linear algebra, this is super simple. It's just it's just this vector times a matrix, and it becomes a vector of another size. That's all. But you know, if you don't know that, it's okay. It's like for in neural networks, this is actually a very convenient thing to do. It's like whatever dimensionality you have, you can transform it into another dimensionality by introducing a set of parameters to do that. Okay. Yes.
When do we need to do these transformations?
When do we need to?
Just
Yeah.
now when we're teaching it, it's
Yeah.
about like, oh, we have this set of vector and then changing it to like the probability. So it should be 1 to 1, right? Then when do we need
So,
to do
for
these?
example here, HT here may, may have a dimensionality. This is the dimensionality for this kind of a hidden vectors for these hidden units. So this probably have a dimensionality of say 5. Okay, but in the end of the day, you have a vocabulary size of say 10. Okay, so you want to produce a vector of size of dimensionality 10, right? Based on this vector of dimensionality 5. And then when you have the 10 dimensionality vector, you can change it using a softmax into probabilities so that you can compute the final loss in the end, right? So this is where you need those transformations. Okay? Okay, so what we have here is by inputting this thing, and then for example the gold next word is student, and then we have this dimensionality of 5 thing, and say we have a dimension we have a vocabulary size equals 10, and then this is like have a dimensionality of 5. Then we will need to transform this thing into a vector size of 10, and this vector to contain the score for each of the word, right? And we know the next word is students. Say students is word number 3. Then we picking this up, right? We're picking this probability up. So for example, the probability is 0.5. Then we compute the negative log on top of this negative 5. And then we can compute the loss there. And then we will be adding it up into the final loss. Okay? So there is a selection inside this thing. If you only have a dimensionality of 5, but you have a vocabulary size of 10, then you don't know what to choose. You don't know what is the correct answer for that, right? So you have to transform it into a neural dice of correct dimensionality before you know what to choose, before you know what to optimize. You want to have this 0.5 number to go larger, right? So basically, if say the word number 2, let's say word number 2 is the word student, then you want this number to be larger, right? In the end of the day. Then what do is you will change these smaller numbers, you will change these kind of things to just make this number larger, right? You will also choose, for example, if I have something here, you will also change this set of parameters to get say x6 prime lower, right? So you want the correct word to have a larger score. You want the incorrect word to have a lower score. Then what you do is you will be changing those parameters. Of course, you will be changing other parameters inside that neural network to achieve that as well, right? Because x1 is also getting from other parts of the neural network. Okay? Better? Okay? Cool.
So I have a question.
Yes.
Can you explain the combination process of the output from the first box A and the X key?
The combination of what?
The output from this box, the A, blue. Yes, the output from this one.
HT minus
no,
1?
No.
Oh, this one?
Yeah.
Ah, okay. So this is a very good question. So this H1 is actually used in both two ways. One is it will be come out to compute this vector so that it can do the loss. Okay. So this H1 also can be inputted into as an input for the second block here, where like combining with this XT, it's computing this HT here. So that's the recurrent neural network.
How to combine them? I see there is a tangent edge.
You can put it into two things. So for example, here you also have the t-1, and you make a copy here and then make a copy here. Okay. It's equivalent to just it's the same as you putting an equivalence operation.
Does that mean it's synchronized?
Does that mean it's synchronized? Synchronized is a very good question. So I will answer another question for you, so you actually know what I mean. So inside, so when we start the back propagation, right? When we start back propagation, the back propagation will go to every single parameter. So for example, if I have a parameter, say theta here, okay, I have the same parameter theta here as well. I have the same parameter theta here as well, right? Then I start to do the back propagation, actually back probes to different copies of the same parameter, right? Everyone can get that? So it's just like in our W1, W2, and B example, we have say our final loss looks like W1x1 plus W1x1 plus W2x2. Okay, so we have two different copies of W1, but then we doing the back propagation, we're doing the automatic differentiation. It actually got like two different gradients into two different places, but the two different places are actually the same parameter, right? So in recurrent neural network, this is a better example. It's like inside these blocks, the parameters, when we do the forward propagation, when we do the forward computation, it's the same thing, right? The same WH, same WE that we are working on in different places, in different steps, right? Everyone gets that? So in each of this block, no matter what is the time step t here, you're actually working on the same computation for the same parameter, right? So you have the WH there and WE there. It doesn't change in the forward pass, okay? But in the backward pass, since that we have actually the same theta inside these different blocks. And you draw the connection there, right? So go from here to here to here to here to here to here. In the end of the day, you go here. So here, 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 go here. Here, 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 go here. The same parameter. So for example, if this one and this one is the same word, if this is cat, and it's actually also the same word embedding, right? So when you do the back propagation, it goes to this one, it goes to this one as well. The two, it's actually different gradients, goes to the same parameter, right? Yes. This is a complete computational graph we have here. So in one computational graph, we only have one loss node, right? This is single loss, single one special loss node here. In RNN, we have different time steps, but in the end of the day, in this larger computational graph, we only have one loss, and this one loss is the summation of loss at time step 1, loss at time step 2, loss at time step 3, so on and so forth, to the end. It's a summation of 3 losses. Okay, so I want to do this guess correctly, I want to do this guess correctly as well, I want to do this guess correctly as well. So it's a summation of loss over different steps. Yes? Okay. How many times the back propagation happened during the entire training? So do you remember though that gradient descent thing? So you go one step, one step, one step, one step until you get to the end. Right? So it happens multiple times. You just, every time step you're working down, every step you're working down until the model actually does good enough. Then you stop the break. You stop moving down anymore, or the parameter doesn't change anymore. Because if you reach the bottom part, the gradient will be 0 and it won't change anymore. So in the forward pass, you compute the loss, and then in the backward pass, you update all these parameters, and then you do another forward pass, then you compute the loss. It's a different loss, and hopefully it's smaller than the loss that you just computed. And then you do the backward pass, then you update the parameters, and then you, based on the new parameters, you compute the loss, and so on and so forth. You do it multiple times. Okay? Yes. After each sentence or after the whole process, what is the whole process? Okay, do we do the back propagation after each sentence or after each corpus level? So we can put a different sentences here, and then we can compute the loss for the entire corpus. Then we can do the back propagate. That's okay. But in practice, we do it on a sentence or like batch level. So we probably have 5 sentences, and then we construct a graph like that, and then we do the back prop, and then we see the next 5 sentences, something like that. Okay, really, really nice questions. I'll have a break of say 10 minutes, then we'll come back.